Hi, I'm Panagiotis Haralabopoulos, and I will present our joint work with Adam Karsmart on single-source shortest paths and strong connectivity in dynamic planar graphs. So let us start by defining the shortest paths problem. It consists in maintaining a data structure over a graph G that undergoes updates, such as edge insertions and deletions, and is able to report shortest paths or distances upon a query. So we usually identify reporting shortest paths with answering distance queries as most known data structures. Upon answering a distance query, can also retrieve the shortest path efficiently, that is in time roughly linear with respect to its length. So we call such data structures dynamic distance oracles. This problem comes in two main variants: the all-pairs one, where the query specifies both the source and the target vertices, and the single source variant, where the source is fixed and the query just specifies the target vertex. Throughout the talk, unless explicitly stated otherwise, we consider directed weighted graphs. We only deviate from this when discussing related work. So let's get on to related work. So what is known for general graphs? For the all-pairs variant, it is known from the 70s that the all-pairs distance matrix can be computed in time proportional to the product of the number of edges and the number of vertices in the graph, which can be n-cubed. And Dimitrescu and Italiano showed that it can be maintained in roughly quadratic time in the number of vertices, amortized time per update. So this tilde notation here hides polylogarithmic factors with respect to the number of vertices throughout the talk. In fact, if one wants worst case update time, then subcubic bounds are also known. So let's move to single source dynamic distance oracles. So no non-trivial algorithm is known for the fully dynamic case. Such algorithms are known only for the partially dynamic case when the graph is incremental or decremental. And this has been explained in a sense by the lower bound of Roddy and Zwick, which says that we cannot have such an oracle that has the same bounds at the same time. Strongly subcubic initialization in the number of vertices, strongly subquadratic amortized update time, and strongly sublinear query time. And this lower bound is conditional on the static all-pairs shortest path conjecture. And in fact, breaking these bounds, even when the graph is partially dynamic and directed and unweighted, would be a breakthrough in this area. And let us note here that for sparse graph, that is when the number of edges is linear or roughly linear with respect to the number of vertices of the graph, there is nothing known that is better than just recomputing from scratch the shortest paths. So there are several workarounds to try and beat these bounds. One is to settle for approximate answers, and indeed a large body of work has been devoted to this task. And the other is to study more structured graph classes. And this is what we do here. So we focus on planar graphs. And let's see what is known. So for the all-pairs problem, it is known how to achieve n to the 2/3 update and query time. And this was first presented by Faxarenko and Rao and extended or reinterpreted by Klein and extended by others to support more updates. And we will, in a sense, see this algorithm of Klein in a bit. And there is a lower bound conditional on the all-pairs shortest path conjecture due to Abud and Algard that says that the product of the update time and the query time cannot be strongly sublinear in the number of vertices of the graph. Let me recall here that planar graphs are sparse for everyone. And Abraham et al. Showed that when the graph is undirected and one is happy with 1 plus epsilon approximate answers, then root n update and query time are achievable. So that's the state of the art for all-pairs dynamic distance oracles for planar graphs. And now let's focus on single source ones, which is the main focus of this talk as well. So for single source ones, it is not explicitly stated in the literature, but this all pairs exact distance circle can be turned in a single source distance circle with n to the 2/3 update time and 1 to the n to the 1/3 query time. And we will show this as a warm-up before we move on to our result. And if one wants to settle for 1 plus epsilon approximate answers, then root n update time and constant query time is attainable, but only for decremental graphs. And this is due to customers. And graph is decremental if the only allowed updates are deleting edges and increasing weights. Okay, so let's move on to our results. So we consider the single source distance circle problem in a dynamic and vertex planar graph, where the allowed updates are edge insertions, edge deletions, and changes of the source. And we saw a data structure that can maintain the graph that can be maintained in n to the 4/5 worst case time per such update, and can answer distance queries from the source S to any vertex of the graph in log square n time. And this is the first single source shortest path algorithm that breaks the O tilde of n update query time product barrier, even in the approximate setting. This is when the graph is fully dynamic. Okay. And somewhat surprisingly, our approach, as we will see later, combined with a few more ingredients, also yields a fully dynamic strong connectivity data structure with the same time complexities. That is n to the 4/5 time update and log square n time to retrieve an identifier of the strongly connected component to which a queried vertex belongs. But more on this later. So let us start with some preliminaries. The existence of small cycle separators in planar graphs implies R divisions, that R divisions are possible. And an R division, for some R, is a decomposition of the graph into n by R pieces, such that each piece has O of R vertices, and the number of boundary vertices of each piece, that is, vertices who also have edges incident to vertices in other pieces, is O of root R. So here is an example. This is a piece, and the red vertices are the boundary ones. Okay, and we note the boundary of a piece like this. And throughout the talk, we assume that all such vertices lie on a single face of P, which is usually called a fold. This is not always possible, but we can always guarantee that they lie on a constant number of faces. And in this work, it does not cause any particular complication. So an R division can be computed in n time, in O of n time. And in particular, as shown by Klein and Subramanian, it can be maintained in O of R worst case time per update. And this maintenance only changes a constant number of pieces per update. So this is what we rely on to maintain our R division. And now I will define the multiple source shortest path data structure, which is the following. So consider a graph G, for instance, this blue piece of our R division. And then we can construct a data structure in nearly linear time in the size of the graph that can answer the following type of distance queries in logarithmic time. So we have a specified infinite face, and here is the face on which the boundary nodes lie, the boundary vertices lie. So given one of those boundary vertices and any other vertex of this graph, it can efficiently report the shortest path, the distance and the shortest path from U to B. So the distance it can report in logarithmic time. Okay. And using MSSP, we can compute the following graph efficiently for a piece. So the DDG of the piece is a complete directed graph on the boundary vertices of the piece, such that its edge encodes the distance between the two vertices. So in order to compute all pairwise distance of the boundary vertices, it suffices to compute an MSSP data structure and query it for all pairs of distances. And then, crucially, what Faxaroinfo and Rao showed is that Given a collection of such dense distance graphs with capital N vertices in total, that is with multiplicities. So for instance, this vertex could belong in the DDGs of 3 pieces, these 3 pieces. We can run single source shortest paths computations from a specified vertex belonging in these nodes, in these vertices of the DDGs, in time roughly proportional to the number of vertices and not the edges. Observe that the edges could be quadratic in the number of vertices. And for instance, when we want to run such a computation on the collection of all DDGs of the pieces of an R division, it runs in time n by root r, because we have n by r pieces, and the number of boundary vertices of each piece is root r. We get n by r times root r, n by root r. And this is the third component I want to define in preliminaries. So we can now move to describing a warm-up dynamic distance oracle. So this is a simplification, an adaptation of Klein's oracle for all pairs shortest paths, and it essentially offloads some of the query procedure to the update procedure compared to his. So we treat an update as follows: an update to the graph. We maintain our division, and we can do this in O bar time. Then, for each of the constant number of pieces affected by the changes in the R division, we maintain an MSSP data structure and the DDG of the piece. And this runs also in time O tilde of R. And then we run FR Dijkstra from our source S in the union of DDGs in time n by root R. Note here that S may not be a boundary vertex, but this is not really a problem. We can maintain some more information for pieces and tackle this. It's just a technicality. So in particular, when we have done this process, we already know the distances from S to all boundary vertices of our R division. And now let's see how to answer a query. The problem is that the query may be inside, may not be a boundary vertex. So first, given the query vertex V, we retrieve a piece P containing V, and let's assume that S and V are not in the same piece, just to make sure that then this ensures that the shortest path from S to V must cross the boundary of the piece P. If they're in the same piece, then the situation is easy. Okay, and then since we can guarantee that the path must cross the boundary of piece P, what we need to do is we want to compute the minimum of this set. And this set, the elements of these sets are for every u in the boundary of piece P, the distance in G from the source vertex S to U, to the boundary vertex, plus the distance inside P from U, this boundary vertex, to V. And the minimum over this gives us the distance from S to V in the whole graph. And let's see how to compute this. So as we said before, we already have this first term of the sum, the distance from S to U in G, since we run FR Dijkstra. And then the second summand can be retrieved from the MSSP data structure for piece P. So overall, by iterating naively through the root R vertices on the boundary of piece P, we pay root R log R time, because we have root R of them. This magenta value can be computed has already been computed, and then the distance can be retrieved in logarithmic time. And if we balance for the update time, we set R to the end to 2/3 and get the claimed bound. We can also get some other trade-offs. So when we make this term dominate R, then we get n by root R update time and root R query time. Okay, so let's now see what can be done more efficiently. So essentially what we're doing is we're naively going over the boundary vertices of the piece containing V, in order to find the last vertex u on the shortest S to V path. And as you can see in this figure. And now, instead of going through all of them naively, we want to just have some data structure that returns this u in nearly constant time. Okay. So, in a way, the distances from S to the boundary vertices of P define a set of additive weights. And now, what Gabrychowski et al. In a paper on exact distance oracle for static planar graphs showed that given this set of additive weights, we can construct a data structure occupying roughly root R space that, coupled with an MSSP data structure for the same piece, can answer point location queries in log square n time. And last year, in a joint work with Gabrychowski, Moses, and Wyman, we saw that this data structure can be in fact constructed in R to the 3/4 time, given some extra auxiliary information for the piece that can also be maintained in roughly R time. I'll not go into these details. And let me try to hint out why this is even possible. So it uses the additively weighted Voronoi diagrams, which has been is a tool that has been used recently since its use by Cabello in the planar diameter problem, in similar problems for static graphs in planar graphs, such as distance oracles. And let me define it. So, suppose that this is our piece, and the boundary vertices are these differently colored vertices on the infinite face. Then we define the Voronoi cell, and they have some weights, additive weights. Then we define the Voronoi cell of its such vertex to be all the vertices of the graph that are closer to it with respect to the additive distances. That is, the sum of the weight, the additive weight, and the distance from this side to a given vertex. Now, because the graph is planar, these Voronoi cells are simply connected. And in fact, because all our sides lie in one face, and by assuming that no Voronoi cells are empty, which we can describe this Voronoi diagram by a tree on root R vertices, irrespective of the size of the graph being larger, being R in particular. And this is the tree that on which the data structure of Gabrychowski et al. Depends on. Just they pre-processed in some way and show how to use it together with an MSSP data structure to answer point location queries. And let me reiterate that it can be built in R to the 3/4 time. Okay. So let's see how to tweak our data structure from before in order to achieve the promised update and query time complexities. So let me recall to you that on the update we maintain the R division, the MSSP data structure and the DDG for each piece, and we run FR Dijkstra from S in the union of DDGs. Then we also do one more step. For each piece, we construct this point location data structure that takes all of root R space, this tree, Voronoi tree, the dual representation of a Voronoi diagram as a tree, and with additive distances, additive weights, the distances from the source vertex S to the boundary nodes of the piece. And we have to recompute this for every piece, as the distances from S may have changed due to the update. Overall, we have n by R pieces changing, and for each of them, we can recompute this data structure in R to the 3/4 time for a total of n by R to the 1/4 time. And for the query, just instead of going naively through the root R vertices, we just perform a point location query. And this gives us the answer in log square R time. And by setting R to be n to the 4/5, we obtain n to the 4/5 update time and logarithmic log square n query time. And yes. So now let's move to strong connectivity and see how these ideas can help us there. First of all, let me reiterate on what the task is. So we want to maintain the graph G, so that given a query vertex V, we can return an identifier of the strongly connected component that this vertex belongs to. Okay, so for general graphs, it is known that we cannot have both the update and the query time to be sublinear, strongly sublinear, unless the strong exponential time hypothesis fails. And for planar graphs, one can use the dynamic plane transitive closure data structure of Dixon-Sankowski, which yields roughly root n update and query time. Observe here that the product is again roughly linear. So let's see what we do. We need one more ingredient, which is reachability certificates, and in particular the reachability certificates introduced by Subramanian, which we have adapted here for our purposes. So let P be a piece of an R division. So there exists a directed graph XP, such that the boundary vertices of P are also vertices in this graph XP. XP has size root R log R, and for any two boundary vertices of P, U and V, you can reach V in P if and only if you can reach V in XP. And in fact, this XP given P can be computed in time R log R. So this can be seen as a reachability sparsifier, and let's see how to use it. So again, we maintain an R division of the graph. We maintain a reachability certificate for each piece of the R division, and thus a constant number of pieces are updated for any update in the graph. This can be also done in O tilde over time. And then we run a textbook strongly connected components algorithm on the graph X, which is defined as the union of all those reachability certificates. And this runs in n by root R time. And now note, as these reachability certificates encode information for G, but just on the restriction on the boundary vertices, given we already have the correctly identified the strongly connected components in which the boundary vertices belong. Then we sort these SECs topologically, again using a textbook algorithm. And we make the following observation. So let B1 up to Bk be some vertices of G lying in distinct strongly connected components. Then some vertex V is strongly connected to some Bj if and only if the following hold. So if and only if Bj is in the topologically earliest SEC reachable from B, and Bj is in the topologically latest SEC that can reach B. And let's see why this is. So let these components in which B1, B2, and so on belong to be sorted topologically as in the figure. So B1 is the earliest one and so on. And let V be some vertex. So first of all, we cannot have this. We cannot have before the component of B4 to be able to reach V and V to be able to reach B1, because then the components are not topologically sorted. In addition, if we have this case, that the latest component that can reach V is B2, and the earliest that is reachable from V is B5, then V is in none of these components, because only B1 and B2 may be able to reach the components of B1 and B2 may be able to reach V, and V can only reach possibly the components of B5 and B6. While in the case that V can reach the component of B3 and is reachable from the component of B3, then V simply belongs to this SCC. So how do we use this observation? So for each piece, we construct point location data structures as before, but now the additive weights, instead of being distances from the source S, they stem from the topological order of the strongly connected components of X. So we want to be able to compute the topologically earliest SEC that is represented in this graph X, the union of the reachability certificates, and the topologically latest SEC that can reach P. So we can do this with these point location data structures. And the update time, the time needed to update this per update to the graph is as in the single source distance oracle. So it's n by r to the 1/4, and by r pieces, each of them r to the 3/4 time, needs r to the 3/4 time. Okay, and then if V is in one of these SCCs representing the union of disability certificates, we're done. However, it might be the case that it is not, and that these point location queries are inconclusive because they don't return the same SCC. In this case, however, we can know that V is in some strongly connected component fully contained in P, because it does not contain any boundary node of the piece. In such case, we can maintain SCC identifiers per piece in roughly R time and report such an identifier. So overall, the update and query times are the same. So let's summarize and conclude with some final remarks. So we saw an O tilde n to the 4/5 update time and O log square and query time data structure for single source shortest paths and strong connectivity in fully dynamic weighted direct planar graphs. The initialization of this data structure requires nearly linear time, and the space occupied throughout the execution of the algorithm is also nearly linear. We also saw a dynamic closest facility data structure. That is, this data structure maintains a set of facilities, and upon a query for a vertex V, it is able to return efficiently the closest facility to vertex V, the one that should serve. Okay, so to the best of our knowledge, this is the first work that utilizes additively weighted Voronoi diagrams machinery in dynamic graph algorithms. And we're hopeful that maybe more problems can benefit from it. So this is the open question, and of course, improving the time bounds proposed in our paper. So thank you very much for your attention.